Hello and welcome to this quick review of enthalpy of solution calculations. It's in response to some questions some of my students have given me about how to deal with the mass in particular of the water and the mass of the solution. So first I'll go through a little bit of review of the background chemistry. So to begin the chemistry we have to understand the definitions behind it first of all. So what I'm going to do is take each of these definitions and apply it to sodium chloride. So taking the sodium chloride lattice, we know that it's comprised of Cl- ions and Na+ ions. So let's now think about how the lattice enthalpy comes in when we begin the dissolving process. What we actually have to do is overcome the lattice enthalpy. In other words, we've got to break up the lattice into its individual gaseous ions. And to do that, we've got to overcome the electrostatic attraction between the oppositely charged ions. So, the energy required to achieve this endothermic process depends on the size of the ion, in other words its ionic radius, and the charge on the ion. And together these two factors make up what we sometimes call charge density. So if we take a quick look at the diagrams on the bottom left of the screen, you can see that we're talking about sodium fluoride and magnesium oxide. And the diagrams obviously show that the lower the charge, the higher the ionic radius, and for sodium fluoride, and for magnesium oxide, the higher the charge, the lower the ionic radius. So what you'd expect to see is that the lattice enthalpy for sodium fluoride is less exothermic than the lattice enthalpy for magnesium oxide. So let's now assume we did this for 1 mole of ionic lattice, back to our sodium chloride. We've effectively created 1 mole of gaseous Na+ ions and 1 mole of gaseous Cl- ions. So this can be written out as an equation, which then takes us to the next stage of the dissolving process, which is called the enthalpy of hydration, or specifically the hydration. So we've got a diagram that shows this. You can take your gaseous ions and mix them with water, assuming obviously a significant excess, and what happens is you get a hydration shell, and each ion gets its own hydration enthalpy, and because it's an attraction, it's always exothermic. And you can obviously therefore write out the hydration of each individual ion as a separate equation. So this process is always exothermic because it's equivalent to an attraction. So if we look at it a little bit more closely, the partially negative oxygen atom on each water molecule in the vicinity of a cation will attract to the cation surface to form a hydration shell. And the same thing will happen with the partially positive hydrogen atoms on water molecules in the vicinity of an anion, a negative ion. They'll do the same thing. So in this way we prevent the positive and negative ions from reattracting and reforming the lattice. So the energy that is transferred when the hydration actually happens is called the hydration enthalpy. And the complete dissolving process involves both of these lattice dissociation or reverse of lattice enthalpy and the sum of the hydration enthalpy of all the ions happening one after the other. So we can also represent it using a Born-Haber cycle because obviously there's some thermodynamics involved. And you can see that in this particular Born-Haber cycle it is indicating that the enthalpy change of solution is endothermic. So whether or not that's the case depends on the balance of the magnitudes or the sizes of the lattice enthalpy and the sum of the hydration enthalpies. So if we were to take the sum of the hydration enthalpy and compare it to lattice enthalpy, if the lattice enthalpy is greater than the sum of the hydration enthalpies, the enthalpy of solution will be endothermic, as it shows in the Born-Haber cycle on the screen. If it's the other way round and the sum of the hydration enthalpies is itself greater than lattice enthalpy, then the enthalpy of solution will be exothermic. So before we start looking at some actual calculations, let's have a think about the effect of the volume of solvent on the enthalpy of solution. So if we consider two identical samples of potassium chloride, such as 3.5 grams for example, so it's important to separate in your mind the difference between the enthalpy of solution, which is measured per mole and therefore remains unchanged, and the temperature change that would result from actually dissolving the potassium chloride in a certain volume of water. So if your 3.5 gram sample of potassium chloride is dissolved in a smaller quantity of water, the same quantity of energy that's transferred as a result is spread over a smaller volume, so the temperature change will be bigger. So then if you put a separate but identical 3.5 gram sample of potassium chloride in a larger volume of water, it's a lower temperature change because the same quantity of energy is now spread over a bigger volume. So you get a temperature change that is lower, a smaller temperature change. So the point I'm making is an appreciation of this ratio is actually important for exams because they'll often ask you to explain this quite clearly. So this worked example just takes the idea we've talked about with KCl a little step further. Put some data in front of you and ask you to calculate the enthalpy of solution of KCl. So as with any calculation of enthalpy that is derived from measurements that are provided, you have to split into two halves. The first half is working out the heat change, and the second is converting the heat change to enthalpy. So we start by doing Q equals mc delta T. And before we go any further, I just want to share a little assumption with you that we're making at this point. And that is that all aqueous solutions have a specific heat capacity very, very close to that of pure water, which is 4.18 joules per gram per Kelvin. So the mass of any solute is included. Any changes in density are negligible at A level. It's a little bit of a fudge, I must admit, but it's just to make it a little bit more simple for advanced level as opposed to degree level or beyond. So for A level, you assume that if it's an aqueous solution, it has the same heat capacity as water, so the mass that you use for the value m is your solute plus the mass of any solvent. So 25 here for the solvent and 3.73 for the potassium chloride that was added to it. So you'll notice at this point that even though 15 minus 22 makes minus 6.5, I'm not yet introducing that idea because I can deal with that a bit later when I do my enthalpy change. So I'll need to be mindful of that a little bit later on in the fact that the temperature finally was lower than the temperature we started with. So it must have meant that there was an endothermic change going on. So the surroundings appeared to get colder, which must mean that the system took on heat. So that gives me 780.5941 joules, obviously keeping my full calculator value for the time being. So now what I can do is convert this heat change into an enthalpy in kilojoules per mole. So the first thing to do is to calculate the number of moles of potassium chloride that we dissolved, and taking the number of grams, dividing it by the molar mass gives us 0.0500 moles. So to work out the enthalpy of solution, you have to divide the value for Q in kilojoules over the number of moles of potassium chloride, which is obviously 0.780591 divided by 0.0500. So that gives us plus 15.6 kilojoules per mole to the minus 1, not forgetting obviously that we had a temperature drop, so it's an endothermic process in this particular case, so it gets a positive value for its enthalpy. So now let's go on and do a past paper question. So this question is about enthalpy of neutralization. So this is similar to the examples that we were looking at before in that it also takes place in aqueous solution. But it's important to recognize it's not exactly the same as enthalpy of solution. It's in enthalpy change of neutralization they want you to write about. So it should be just simple, straightforward recall at this point. So it's obviously the enthalpy change when 1 mole of water is formed from the reactant acid to the base with all reactants and products in their standard states. So then it says the student measures out 35 centimetres cubed of 2.40 moles per decimeter to the -3 of sodium hydroxide and 35 centimetres cubed of 2.4 moles per decimeter to the -3 of HCl. And it says the temperature of each solution is the same. So it says the temperature rises by 16.5 degrees C. So don't forget that means that the enthalpy change is going to be exothermic. So it also tells you that the specific heat capacity of the mixture is 4.18 joules per gram per Kelvin, which allows for the presence of any dissolved species like we talked about a bit earlier. So I'm going to move the page down a bit to make some room for the calculation, which, taking into account the combined volume of the two mixtures, 35 of NaOH and 35 of HCl, the total volume of the whole mixture is going to be 70 centimetres cubed. So therefore the mass is going to be 70 grams. So because everything is equimolar, we can assume that the number of moles of water upon which our enthalpy is going to be based is the same as the number of moles of HCl and the number of moles of NaOH. So the number of moles of sodium hydroxide, for example, is going to be 0.0840 moles. So to work out our delta newt H, we take our value of Q in kilojoules, so it's 4.8279, divided by 0.0840, that gives us 57.475. Obviously not forgetting the correct sign, because it's an exothermic change. Because if you remember, the temperature rises by 16.5 degrees C. So let's do the next bit of the question now. I'll just move the page down slightly. And it says the student repeats the experiment using 70 centimetres cubed of 1.20 moles per decimeter to the -3 HCl instead of 35.0 centimetres cubed of 2.40 moles per decimeter to the -3 HCl. So the first thing to check is that the new quantity of HCl, how does it compare to the old quantity of HCl? So a quick check mathematically and you'll be able to see that it's the same amount. You probably wouldn't have had to have done a calculation here because you can see it's double the volume and half the concentration, so the moles remain the same. So that means you'll get the same energy released but into a larger volume of water. So as the question says, that means the temperature rises less. But how much less? To work this out, you've got to rearrange Q equals mc delta T so that delta T is the subject of the equation. So this means we divide 4827.9. So that gives us a temperature rise of 11 Kelvin, which equals 11 degrees C in total. So it's worth for a second qualifying that as an increase of 11 degrees C, not an absolute temperature of 11 degrees C. So I'm not taking into account the difference between the Celsius scale and the Kelvin scale, because an increase of 1 Kelvin is the same as an increase of 1 Celsius. So 11 Kelvin equals 11 degrees C increase. So hopefully this has been a useful clip going through some of the bits and pieces surrounding enthalpy of solution and how you use it. I know I went on to use an enthalpy of neutralization example at the end, but that was just to illustrate how it can transfer over into other enthalpy changes that take place in aqueous conditions. So for now, thanks a lot for listening, and until next time, see you soon.